Hello guys, it's Johnny time and welcome to another smart contract hacking tutorial. Today we're gonna solve the 10th Damn Vulnerable DeFi version 4 challenge FreeRider, and we're gonna do it with Foundry because this is the newest, most recent version. In this challenge we have to hack an NFT marketplace and it's gonna be super interesting and insightful. So without further ado, let's get started. FreeRider Challenge 10, a new marketplace of damn valuable NFTs has been released. There has been an initial mint of 6 NFTs which are available for sale in the marketplace. Each one is at 15 ETH. Okay, quite expensive. A critical vulnerability has been reported claiming that all tokens can be taken, yet the developers don't know how to save them. Okay, they're offering a bounty of 45 ETH for whoever is willing to take the NFTs out and send them their way. The recovery process is managed by a dedicated smart contract. You have agreed to help, although you only have 0.1 ETH in balance. The devs just won't reply to your messages asking for more. If only you could get free ETH, at least for an instant. Okay, so we have a marketplace with NFTs that are priced at 15 ETH, 6 NFTs in total. We need to steal them from the marketplace we don't have 15 ETH, but we got a hint here that if we could just have it for a slight moment, flash loans or flash swaps, then if we get all the NFTs and send them to this special smart contract, we get 45 ETH, and this is our goal, to earn this bounty. So let's take a look at a marketplace and try to find any bugs or vulnerabilities. So this is the marketplace contract. It defines some state variables, tokens, offers count. It saves the current offers in this mapping that maps between token ID to its price. So you can essentially offer some ETH for NFTs. It defines these events and these errors. In the constructor, it essentially gets an amount of NFTs that we want to mint. It deploys the NFT contract, renounce ownership, so you cannot upgrade a contract, you cannot do anything, you cannot change the owner, there is no owner to the contract. And then it essentially mint to the deployer these NFTs, the amount that he sent in the constructor upon deployment, and set the token, NFT token contract address. We have this function called offerMany and offer1, which allows us to list NFTs in the marketplace, set their price, and ask for this price. So offerMany gets token IDs and prices to arrays. It makes sure that the arrays have items, and both length of the arrays, they have the same amount of items. Then it essentially calls in this for loop every time this offer1 function would get one token ID and one price. You check that the price is not 0. Check that the message sender, the one who called this function, is actually the owner of this NFT. Make sure that he approved this smart contract to spend this NFT, so we can use the transfer from function, or we approved this smart contract to spend all his NFTs. And then it registers this offer in the mapping and do a simple assembly, just count, increase the count by 1. That's what it does. This changing the storage slot to, this is YUL code, assembly code. So it essentially increases the current value at slot 2 by 1, which essentially the slot 2 is going to be this offer count, because slot 1 is going to be this, and probably slot 0 is the re-entry guard state variable. So this is going to be slot 2. So it essentially increases this number by 1 every time. And at the end, it emits an event. Then we have this buyMany function that receives tokens IDs, and then it calls in for loop this buy1 function. Now note that this function is payable. So when we call this function, we have to send some ETH to the contract to buy the NFTs, and it's also non-reentrant, so it's protected from reentrancy attacks. Then we call this buy1 function every time with different token IDs, depends how many token IDs we passed in the array. And I already left an audit issue here, which is going to be the hint of the bug. We'll check it in a second. We make sure that the price to pay is not 0, which means that the token is actually listed for sales. If the token ID does not exist in the mapping, then this will be 0 and we'll revert the transaction that because the token is not offered for sale. Then you check that the message value is greater than the price to pay, because if it's lower, greater or equal, because if it's lower, it's going to revert with insufficient payment. Now, I left an audit issue here, which is actually critical vulnerability with this implementation and this smart contract. And the thing is that when you call this buyMany function, you pass multiple amount of tokens that you want to purchase in a single transaction. It could be one, or it could be also 100 tokens. Now, then it calls this buy1 internal private function. And every time we check the message value, we have to remember that the message value is going to be the same through all the iterations of this for loop. And what it essentially means that we can send the price only for one of the tokens. Instead of paying for 10 tokens, we can pay only for one, because the message value is going to be the same. So let's say one token costs 15 ETH, which was written in the README. We can just send 15 ETH to this function and pass here, let's say, all the 6 tokens. And then this check will pass, because in every iteration, message value is going to be the same, price to pay is going to be the same. It's still going to be enough. It's going to be 15 ETH, but the contract, this function is not aware that we're trying to buy 6 tokens, but it thinks that it's only one. It's only checked it for one specific token. So we can trick the smart contract that way by paying only for one token, but requesting to buy multiple tokens. Then we change the state. We decrease the offer count by 1. I'm wondering why here we don't use assembly, but here we do use assembly, just some small stupid thing. We could use assembly here as well if we want gas optimizations. And then we just transfer the NFT from the smart contract, which is the owner of the token, to the message sender. So we're essentially sending the NFT to the buyer, because he wants to buy it. So we transfer the NFT and we send. Okay, I have to stop you here because I made a small mistake. So the thing is that this smart contract is not going to hold the NFTs. It just checks that it has an approval to spend those NFTs. So when someone lists an NFT, he needs to approve the smart contract, which he checks the approval, lists the NFT, but it doesn't take the NFT and hold them in the smart contract. It's still in the original buyer. And that's what happens here. I just figured it out while checking the buy1 function, because it essentially transferred the NFT from the owner, and the owner is not a smart contract. I made a mistake when I said that. It's actually the seller, the one who listed the NFT, and it transfers it to the buyer, and then it transfers the ETH, the price to pay, to the seller. So the smart contract is not actually holding an NFTs, but it's just an intermediary between the buyer and the seller, which makes me think that there might be another issue. What if I list an NFT here as a seller and I give an approval, so it updates the state, and then I just revoke the approval? What happens? So I always wanted to think like hackers, like how do you break things? How do you make unexpected cases in the state? So a seller can essentially just offer an NFT, then approve the smart contract to spend it. The smart contract is not going to use the approval until someone buys it. It's going to update the state. The NFT is going to be listed, available for sale. But then the seller is going to revoke the approval. So when someone tries to buy the NFT, the operation will fail. This is an easy medium in an auditing contest, but it's not very related to this challenge. I know that at this point, you might think you lack some technical knowledge to understand all of this with ease. That's exactly why I created a smart contract hacking course. Instead of piecing together scattered resources, you will follow a structured learning path together with hands-on exercises that simulate real-life attacks. When you get stuck, our Discord community with security researchers and fellow students is there to help. And once you've mastered everything, you will earn an official certification to validate your skills. Transform from watching tutorials to actually understanding smart contract security. Visit our website to start your journey today. So now that we understand how the marketplace works and we saw a vulnerability where we can pay for one NFT but get multiple of them, let's see how the FreeRider Recovery Manager works. This is a simple smart contract that essentially has this on ERC received function. And it tracked how many NFTs it received. And once done, then it sends the bounty to the recipient. So our goal here is to send all 6 NFTs to the smart contract to win this 45 ETH. So all good, we can pay for one NFT and get all of them, but we don't have 15 ETH. We have only 0.1 ETH, remember? So we need to access another source of liquidity just for a slight moment to be able to purchase at least one NFT. And once we purchase all the NFTs with the price of one, then we can get the bounty and then pay back the liquidity, the price that we pay for the single NFT 15 ETH plus some kind of, I guess, flash loan or flash swap fee. So because we have this 45 ETH as a reward, so we have enough money to pay back the loan plus a fee. And if we go to the test file and we observe here the setup, we see that there is some kind of Uniswap pair with some 15k tokens and 9,000 ETH in reserves. And anytime we see Uniswap pairs, it also means flash swap. So all this liquidity is available for us to take a flash swap. And if you want to dive deeper into flash swaps and flash loans and all these advanced topics and cool, super interesting subjects, please check out the smart contract hacking course, the structured best learning program out there. Also get access to the community, to the certification. So definitely go ahead and check it out. So long story short, we can use this pool to take a flash loan, take this ETH liquidity for a slight moment, use it to buy a single NFT while taking all the NFTs. And then we get the bounty, we send the NFTs to the recovery account and eventually pay back this 15 ETH flash swap plus 0.3%, which is the usual swap fee that is in Uniswap contracts, in Uniswap V2 pairs contracts. And this is exactly what I did here. I created this attack free rider contract with the pair address, marketplace address, Uniswap pair, marketplace, NFT marketplace, wrapped ETH, NFT token address, recovery account, and player. We have the constant of the NFT price, which is 15 ETH, and an array of all the 6 token IDs from 0 to 5. In the constructor, we set all the state variables, and this is the start function. This is where we initiate and start the attack. The attack will start when we request a flash swap of 15 ETH from the Uniswap V2 pair. So this is the NFT price, it's 15 ETH, and we call the swap function. By default, the swap function in the pair contract in Uniswap is a flash swap. It's supporting flash swaps. And if you don't know it, it means that you didn't go through the AMM's chapters and DEX's chapters in the smart contract hacking course. If you do, I'm proud of you. Then another thing that you will learn in the course is that once we do a flash swap, then the Uniswap per smart contract is going to call this Uniswap V2 callback function, which we, the requesters of the flash swap, need to implement. We do some fancy access control here to check that the sender, the one who called this function, is actually the Uniswap per contract, and the initiator of this transaction, the one who actually called this attack contract, is the player, so no one can manipulate our attack contract. Then here we get wrapped ETH. We don't get native ETH, so we need to call the withdraw function in the wrapped ETH contract to get native ETH, which important to understand that we need to implement after this call. We need to implement this callback function, both when we sell the NFTs and also when we unwrap wrapped ETH to ETH. So when we unwrap the wrapped ETH to ETH, we need the receive fallback function that the contract will be able to receive the ETH. This is exactly what happens here. So we get the ETH, and then what do we do with this ETH? We buy the 6 NFTs. So we pass all the tokens array 0, 1, 2, 3, 4, 5, but we pay only for one, only 15 ETH. We call the buyMany function. After we purchase 6 NFTs in a price of 1, we want to send them right away to the recovery contract to get the bounty, and then we get this bounty, and with this bounty we essentially pay back the flash loan. So the amount to pay back is the price, the initial price that we borrowed, 15 ETH plus 0.3% swap fee, and we give a little bit more, 0.4 just in case, so we won't break the K and the constant product formula. So we're just having a bit of a buffer here. So we calculate this amount to pay back. We convert it from native ETH to wrapped ETH, and eventually we transfer this wrapped ETH to the pair Uniswap pair contract to not break the K. And we have this also on ERC 721 received function, so we're able to accept and receive these NFTs in safe transfer from function, so it won't be reverted. We have this callback to receive when we unwrap the wrapped ETH to ETH, and also when we get the bounty, because I think when we get a bounty, we get it as native ETH. So we need somehow as native ETH. We need somehow to receive it. This is how we receive it over here. And now everything looks good in the test. All we do is just deploying the contract with all the parameters. So all we have to do in the test function is just to deploy the attacker smart contract, send here some ETH for the flash swap fees, and also pass all the relevant parameters, call the start function, and then all the magic is going to happen from there. So let's run the FreeRider test, and we can see that we completed the challenge because all the tests passed. Congratulations guys, you completed the 10th Damn Vulnerable DeFi version 4 challenge. If you enjoyed this video, make sure to like this video, subscribe to the channel, ask your questions in the comment section below if you have any questions. And if you want to take your career seriously in smart contract security and auditing and hacking, consider joining our community and enrolling into the complete smart contract hacking course. Thank you so much, and we'll see you in the next one.